x1, and from the x1 we find x2, x3, and so on, and eventually this may converge to the solution. So this was the idea we covered last time, and to do this iteration we need some kind of assignment step. In other words, xn is here, right? And then the next point should be here, right, generally. So from something we get something here. So x is determined by some function g of x. So g of x determines new x. So this is the scheme. And how to determine this is the research or theory. So we already learned the important or famous cases how to determine x. And if you have a question up to this point, ask. The next, yes?
Can we talk about the iteration method just briefly again?
Iteration method is using this thing repeatedly. In other words, initially we use starting point x0, and then if we plug this into g function, then you will get g of x0, right? So we call this x, new x, right? And then we plug this in here, then you will get g of x, right? And then this becomes x, and so on. So we are using xn plus 1, x0 in some, but in programming you can just use x. X goes into g, and then creates a value, and it goes into g, creates value, and so on.
All right, thank you.
Other questions? Then the next thing is the idea of using second order function. Up to the point we use the straight lines to cut the horizontal line. So instead of straight line, we want to use a parabola. So parabola cuts the line. In other words, we want to use the second order function to cut the line. Usually second order function can be determined by 3 points: x0, x1, x2. These 3 points determine a parabola. Then this parabola passes through the horizontal lines somewhere. Let's call the point x3. So essentially this is the set. These 3 points determines new point x3, right? These 3 points determines new point x3. And then after determining x3, we reassign the value. So it's good to use new x0 instead of this one. And then this becomes new x1, this becomes new x2. And then using this input, you can determine x3. I mean new x3. It's different from the previous. So using the first set, we get the next value. Then with 2 values from the first set and the new value with new assignment, using these 3 we get the new value, and then using these 3 we get the new value, and so on. And eventually we can check whether the new point is close enough to the previous point. So this is the strategy. And the formula is given. Instead of writing down the formula, I will show you the formula from the web. So this is the formula, but I will describe the formula in detail very soon after copying and pasting this formula portion. So this is the formula that we need to use. This is the formula that we need to use, and I will copy this thing. So we determine the formula, we determine the next point, x3, using this formula. So initially we had x0 point, x1 point, x2 point, right? We had 3 points. And using these 3 points, we determine x3 point following the formula, and I will analyze the formula very soon. So a new point is found, right? And then we iterate these things over and over again, and then we eventually arrive at the solution. So other than the details, any questions, especially idea part? So your program has x0, x1, x2, determining x3, right? And then after determining x3, you reassign, right? x1, that was x1, x1 now become x0, right? x2 now become x1, x3 becomes x2, and then using these 3 inside this, we get new x3, and so on. Then let's go to the formula. F is the equation part, so I will go to the full description here. So what we do is this one. We are solving a function. We are I will write it. We want to solve an equation. We want to solve an equation f of x equals 0. Right? So f of x is given by the problem. For instance, we want to solve this equation. Then, what is f of x? And f of x is the left side, right? So the function f is given by the problem. Sometimes this, sometimes that, right? So f of x is a problem. Then we solve the problem by using the formula. So let's return back to the formula. As you can see, the function is given by the problem, right? This point, and then x2 is the initial starting point, right? There are triple points, right? And we use this one. And w will be explained very soon, and this will be explained very soon. So there are 2 things I will explain. So I will explain this first, and then this one very soon. We will define this convenient notation. In numerical analysis, we will see this kind of thing many times. x1 and x2 are arbitrary. So we will see this kind of difference, divided difference, many times. But it's very inconvenient to write these things over and over again, so they developed the notation doing this. So this is the notation. So once you see the notation, it's nothing but the divide difference. And after this, they generalize this for any number of points. So instead of just 2, they defined 3. F of x1, x2, x3 is equal to f of x1, x2 minus f of x2, x3 minus x1 minus x3. So we can define this kind of way to shorten the expression. And there is bigger reason that I will explain once we go to the section handling these things thoroughly. But right now this is enough, just the definition. So let's practice a little bit. Assume that f of x is x cubed. So assume that this is a function. Then what is f of 1, 2? F of 1, 2 is what? By definition, f of 1 minus f of 2 over 1 minus 2. And f of 1 is 1 cubed, f of 2 is 2 cubed, 1 minus 2, and 1 cubed is 1, 2 cubed is 8, and 1 minus 2 is negative 1. So it is negative 7 over 1, 7. So f of 1, 2 is found. Please find f of 2, 3. F of 2, 3 is what? Please find f of 2, 3. Did you get this result? So f of 2, 3 can be found. Then the next challenge is finding this. So please find f of 1 to 3. F of 1 to 3 is what? By definition, f of 1, 2 minus f of 2, 3 over f of 1 minus 3. Right? I just follow the definition. Then this gives us 12, 2, so it is 6. So you can find the divided differences using the definitions. So we are almost ready to use these things. But before going any further, we want to determine W. And usually W is determined by this definition that I will write down. W is this definition, right? It's the definition. F of 1, 2 minus f of x0, 1 plus f of x0, 2. So this is the definition of W. So you can find this thing, you can find this thing, you can find this thing. So please browse the definition browse these kind of definitions, right? We are defining, and you can check and ask questions. So all these things are numbers. All these things are numbers. And using these numbers, you can now return back to the formula to determine the second point. Take a look. F is given by the problem. X2 was chosen by you, right? This is the initial value or derived value. You chose these numbers. And W is determined here. W is determined here. And f also is determined by the given function and x2. And then f of x0, x1, x2 is determined. So the only thing remaining is the max portion. But other than this max portion, everything is done. Any questions? Yes?
In all these examples, you kept on saying you kept them in order. Does it matter? Does x0 have to be less than x1, has to be less than x2, etc.? Are they completely arbitrary? So
good question. Very good question. Generally, f of x1, x2, x3, x4, we can extend anyway, right? x1 million, and can be shuffled anyway. Can be shuffled anyway, x99, x100, and then x1, x2. Shuffled anyway, and it will be the same, generally. So no matter how you order, the result is the same. Yes?
As long as those don't ever equal each other?
What do you mean by?
Well, we're dividing by x1 minus x2, so as long as they're not equal.
I see. That kind of repeated case will be covered later.
Okay.
That kind, a little bit different definition exists. So in the first place, we don't have repeating x1 up to x1 million. We don't have in this definition, but later we will broaden the definition to include repeated points later.
So when we're, running this through like a loop or something like that, these values won't get so close to each other that a computer can't tell the difference between them?
Good point. So when you program, you should be very careful, because initially when you choose these 3 points, very, very important point he mentioned in implementation. When you choose these 3 points should not be too close, right? There should be some kind of distance in the first place. In other words, you choose this 0.5, then you may choose 0.6, and you may choose 0.7. But you don't choose 0.5, and then you don't choose 0.5, 0.0000001. You don't choose that, right? So you choose these things a little bit separate. Good point. Any other questions? But theoretically, no matter how you write, they will be the same. In other words, I will write an example. For any function, f of 1, 2, 3 will be the same. F of anything, 3, 1, 2, or 3, 2, 1, or 1, 2. Anyway, it's okay. Theoretically, it's completely proved. Of course, if I prove it in class, it may take about 2 sessions. So if you want the proof, you can come and I will either show you or give you the manuscript having the proof. Any other questions? Then we are almost ready. Then finally, max. Max comes from this idea. Maximum magnitude. So I will write it this way. Usually comes from complex numbers. Complex numbers. So we measure the size of a complex number by using Pythagorean theorem, and usually, I'm not just saying max, generally, we want to find the norm of this kind of thing, and usually it comes from a squared plus b squared. So this could happen. A is like 3.2i and plus minus 1i. So this kind of situation can happen because we are, oh sorry, I should use 1 sign here, not 2 signs. Here as you can see in the formula, we have plus minus signs. We have plus minus signs. Do you follow me? We have plus minus sign. Because of this plus minus signs, we may encounter this kind of situation. Right? We may encounter this kind of situation. Then we consider the magnitude of this separately. So if we use plus sign, then the magnitude is 3 plus 2i plus 1 plus I gives us 4 plus 3i. Do you follow me? This is the magnitude of this plus, I mean the plus case. Then what is the magnitude of this one? It is 4 squared plus 3 squared. Then it is square root of 25 or 5. So the magnitude of this case is pi. Assume that we use minus here. Then 3 plus 2i minus 1 minus I gives us 2 plus I. Then the magnitude is what? It is 2 squared plus 1 squared, square root of 5. What is bigger? Top one is bigger. So when we have 2 different cases in the denominator, you check what has a bigger magnitude, and then use the bigger of the 2. Not the magnitude, but the value. So if this happens, so if computer checks, right? If this is bigger, right? If this is bigger, then your your thing looks like some f of something, and then instead of minus, your thing should be 3 plus 2i plus 1 plus I, right? Because this magnitude is bigger, we should use this value in the denominator. So this is the point of the max notation. So I analyzed all the details and I will return back and then review one more time. So let's return back. So take a look. We use previous points, x0, x1, x2. So x1, x0, x1, x2 are used here. And then, as you can see, f can be calculated, w can be calculated, w minus this can be calculated. And because of this square root, we may get complex numbers here, right? Square root may lead to a complex number. So complex number may appear here. And then it has plus and minus. So you should consider both plus and minus case, and then check the magnitude, right? And you should use bigger of the two. In other words, if plus gives us bigger magnitude, then you should plus in the denominator. If minus gives you the bigger magnitude, then you should minus portion to get x3. Why? Because of complex numbers. So, any questions about Millman's method? So this is it. Then we are done with the techniques, and we will cover theoretical parts that might be a little bit interesting to some, not all of you. Some of you. So. Yes?
Are you going to put these notes on the web, like you did for SciComm?
I will check whether they will have that kind of storage. So, up to this point, we learned about methods. So, for instance, from x0, we find the new x, right, x1, and from x1 we find new x and so on. So we now know how to do these things with different methods. But we want to check whether these things will converge. In other words, if we create some algorithm depending on some method, will it converge? In other words, will we get a solution or not? That kind of thing. And there are some criterion that you can use, and I will use web to show you. So essentially, these three things are required. So I will take the photo of these things and then continue. So convergence comes from these three things. So we are handling the problem this way, right? Using g of x function, we're using g of x function. From x we get new x, right? Using g of x function, we are getting new x. So essentially we are repeating this thing over and over again. Then when will it converge? When will it converge? And the nice condition is this. When g of x is between the interval a and b, g of x result doesn't go out of bounds, right? Doesn't go out of bounds, a and b. In other words, if you apply g of x, then it is still inside the interval a and b. The second thing is, the derivative of g of x is continuous inside this a and b. And finally, the derivative absolute value maximum is less than 1. Then it converges. So this is a little bit limited but strong condition. So roughly this is the condition of convergence. So if someone asks you whether your method converges or not, then check these things and then change your method so that all those your methods satisfy all these conditions, right? Your method satisfies all these conditions. Then you can say absolutely you do converge.
Can you give an example of how you actually use those?
Excuse me?
Can you give an example of how you use those terms?
For instance, I want to check whether this can be solved when x is between like 0.1 and 0.9. So I want to check whether this problem can be solved inside this interval a and b. So let's check it. First of all, if you use cosine x and here between 0.1 and 0.9, then you will get the result between these two numbers. Because it's cosine, I cannot directly show you, but the result after plugging this into cosine will stay inside this interval. Is that okay, or do you need more explanation using graphing tools and so on?
In other words, the result of the function always remains in between the bounds.
Right, right. And the second thing is the derivative. If you differentiate g primed, then of course cosine derivative is negative sign is continuous, right? Inside this interval. So it's okay. And finally, the derivative of this is negative sine x between this and this cannot exceed 1. Right? Cannot exceed 1. The absolute value cannot exceed 1. So this, in other words, this will have a solution. If you iterate this, in other words, I will, for instance, if you start at some point like 0.4 and then use the value cosine 0.4, then you may get some number, right? 0 point some number, right? And then use this value to create cosine 0 point something, then you may get some number. Of course, very soon I will open MATLAB and try to get these things and show you the idea of this theorem. But then eventually we can continue and it will converge. So this is the theorem of convergence. Even in higher dimensional cases, we can do these things. So let's open MATLAB and then show these things. X equals, too fast, I wait. X equals cosine 0. X is equal to 0.4. This is the start, right? X is 0.4. Now, new X is determined by cosine previous X. Do you follow me? So previous X determines new X. So I will do it. The new X is this one. Oh, unfortunately, it went out, so my boundary wasn't great. Sorry. So you can extend the boundary. I'll fix it. So it's 3. So if it goes under bound, then I will add one more. Then the next thing is doing this, right? Cosine X. And the next thing is doing the same. So we are doing the same thing over and over again. And the next thing is doing this. And next is doing this. So you should know the x's are not the same. I used x here, I used x here. These x's are not the same. This x comes from this x, right? So previous x comes into this place and creates new x, right? So new x is created. Now this x comes into this place to create new x. But in any case, we are doing these things. So if you think it converges, then please stop me. I'm good at typing, so you can stop me anytime, but I don't mind typing this all the day. Still not converging. In fact, someone gave me the solution this way. She wrote down many of these, and she might cut and paste. She might copy and paste, but gave the solution like this. That is way smarter, right? That is way smarter. So now see the convergence, right? Yeah. So sometimes when people is good at something, then miss the point, because I was good at typing. I missed the easy things. So you should not rely on your strengths too much. In any case, it converges, right? You see, these are the evidence. Any questions? So I somehow thought it cannot exceed 0.9, but it exceeded. But in any case, you find nice intervals such as A and B. So these are all artificial. You artificially create this kind of interval containing the end result, right? Between these boxes, the result comes in. And then you do.
You could pick any initial point that's in the...
Sometimes it may go out like this, right? You initially assume that you initially chose 0.8, but suddenly it jumps out. Then you change it, because it's theoretical thing. We can do the cooking, right? Any other questions? In other words, this A, B are arbitrary, right? You may pick appropriate interval of your choice to somehow contain the jump, right? It jumps back and forth, but you can contain it. But after containing it, you develop the theory. If it cannot be contained, then it may not converge, right, in the first place. When I taught my son how to multiply, he was very good at adding. He never learned multiply. So all the time I ask him to multiply 9 times 2 is what he has. 9 times. I reversed the problem. 2 times 9, then he added 2 9 times. 2 plus 2 plus 2 plus 2, 9 times. So sometimes something, you are good at something, is bad for other things, in learning especially. So do not rely on one thing too much. The biggest advantage of modern education is this. Modern education, in fact, focuses on breaking that kind of habit. Every people have some kind of habit of staying on their shells, right? But easily, the modern education breaks, especially math courses break those. The next thing is about the way we analyze our things. And if you read the web page, especially having this portion, you can easily find the proof of existence and the proof of uniqueness. So you can find the proof of existence and uniqueness by following these things. And the details are all explained. But after reading these things, if you have difficulties, you can email me or question me. So only one thing remaining, that is 18 extrapolation. Somehow, you saw many different methods. For instance, by using Newton method, you found 0.9, and then, for instance, 0.89, and so on, right? Assume that you used one method to find this kind of numbers or sequence, and the other person used a different method and then determined like this, and so on, right? Assume that there are 2 different methods used to determine these kind of sequences. Then what is better? So we want to check what is better, and to do it, the next one, Aitken extrapolation were developed. So from this, we call this, I will show you, we call the points xn set, right? Xn set. And then from the xn set, like this, from the xn set like this, from the xn set like this, we determine new x hat set, right? X hat set. Right? X hat set is found. So I will make up, and then instead of making up, I will use the result from the MATLAB calculation. So this is the sequence that I produced using iteration method. So I will pick real xn set. 0.4 was the first, and then the next one that I found was 0.9211. 0.9211, and from this I find 0.6050, and from this I find 0.8, and then you can continue, right? You can continue. So these kind of this is the xn set, right? So we say x0, x1, x2, or x1, x2, x3, and so on, right? So we just number them, right? Then from these things, this is the set xn, right? This is the set xn. From this, we can get xn hat set. Xn hat set can be found. So using these three, we can determine the next one. So let's go back to the formula part. But I will pause and then go to the formula part. And using the formula, I will find the first x hat and hat set. So formula says this. We need to determine xn. We need this xn minus 2 value, xn minus 1 value, and xn value. So we need 3 consecutive values, including the same position, right? So including the same position, we need 3 consecutive values. So to determine this thing, the first thing that you can determine should come here, right? The first thing that you can determine should come here. Including this thing, we need 2 more previous. So using these 3 values, we can determine x2 hat, or you can label anyway. Assume that you call this x1, then x1, x2, x3. So it depends on your choice, right? It depends on your choice. You can index any way you want, right? You can index it anyway. In my case, I use x0, x1, and x2. So I can determine, for instance, let's say I don't even want to number the point, because if I number the point, you may stick to the point. So I'll just write the result instead of numbering the point. So I will copy this part so that I don't have to return back and forth. So I will just snapshot this thing. Where is the good place? Maybe here. Very short-sighted idea, but I don't have enough space. In any case, this is the idea. Then, let's write it. So this point is determined by this formula, and this formula says point, I'm doing this part, 0.6050 coming from this, minus 0.6050 minus this number, 0.9211 total thing squared over this thing, xn, that is 0.6050 minus this number, 0.9211, minus this number, 0.9211 minus 0.4. So I could determine this number here, right? This number. And I will use MATLAB to really calculate this number. And then after calculating this number, you can calculate the next number. You can calculate the next number. So after calculating it, you can calculate the next number from this point, the same way. Do you follow me or not? So please write the next number on your own. I want to make sure you can find the next number. This is one number, and please find the next number aligned to this number. So this number, aligned number should be found. So please find this number. Please find the, these are called Aitken extrapolation. So please find the Aitken extrapolation related to this number. Yes?
Is there a specific reason why that's, the denominator is written like that? It seems like you just kind of simplify that.
It's possible to simplify. People used to write it this way, so I just follow the expression. Sometimes they might have some subtraction table in different column. Subtraction of xn and then the previous column, then they may just recycle the. But you can subtract, you can simplify it if you want. Like this minus 2 times this and the plus this. Yeah. But as I mentioned, my suspicion is having more columns in their table. In other words, they might have table of the difference, right?
Right.
Then with the table, the difference written here, difference written here. Even the formula doesn't include that kind of, doesn't capture right. So did you find this thing exactly? So you can find this kind of sequence, right? So initial sequence is found, and you can find Aitken extrapolation sequence, right? So this is Aitken. Then this will show you what behaves better. If you have a better method, then it will be better. Yes?
So doing this way is better than trying to get x1, x2, x3 all the way to like x20 or something like that?
It could be that way too, but mostly not to better the method, but to analyze. In other words, we create x0 to x20 anyway in the first place.
Right, okay.
And then we analyze it using this. Instead of bettering these things using these, but it can be mixed together too. But we are not interested in mixing these things. In other words, we find one method to determine all the values in the sequence. x0 to x20 is all determined by using just one method. And then we don't care what is going on. We just find Aitken extrapolation using this formula. In other words, in this sense, it is unique. But if you develop something, you may use this kind of results to somehow make it converge fast, right? Things like that. It's possible, but we are not improving algorithm. We are just studying about the approach. Yes?
So this would give us a set, the x hat set.
Right. X hat set is uniquely determined in this sense.
And then we compare that to an x hat set for a different method.
Using different initial value. In other words, we used this sequence to create this one. But if you use the other sequence like this, then we make a different sets.
Right, and so we're trying to determine which method is better.
Right.
So how do we compare those X?
If you see the numbers, then convergence is faster.
Oh, they converge faster.
Yeah.
Versus that.
Yeah. So I will, in fact, show you very soon, after explaining all the aspects. So before going any further, I will write, about this time it's good to write program, right? But still this is okay, so I will just hand calculate the stuff. So for convenience, I will use x1, x0, and so on. So x, for convenience, it's not x1 is 0.4, x2 is 0.9211, x3 is 0.6050. So and then x4 is 0.8225. Well, for convenience I did it, because I don't want to write down these numbers over and over again. So I did it. Then to calculate x hat, right? First x hat, I used this thing. x2 or x3 minus x3 minus x2 squared over x3 minus x2, x2 minus x1. This is the formula that I directly apply. So I got this number. This is x hat 2, or x hat 3 in this sense, right? 1, 2, 3, then this is x hat 3 in fact. I just said x hat, but this is x hat 3. Do you follow me? Then x hat 4 will be calculated. X hat 4 is using this 4, 4, 3, 4, 3, 3, and then 2. Do you follow me? Then this is x hat 2. So we can calculate x hat 3, x hat 4, x hat 5, and so on. So we have the given sequence from one method. Now we have Aitken extrapolation. Then as you can see, the convergence is unexpectedly faster. Do you already see it? Do you already see it? X hat at this point, x hat at this point is already very close to the solution, contrary to the method itself, right? X hat here is very close, very fast.
And how can you tell that it's close to
Once it converges, x hat like 5 and 6 might be very close to each other. So once it begins to converge, you can see the convergence. In other words, there are two ways of judging whether it goes to solution. One way is checking whether the height is close enough to the solution or 0. That is one method. The other is judging the distance between the previous one and the next one, right?
Okay. Yeah. And that's what x hat.
Yes, right. Any other questions? So you can, as I showed you, no matter what sequence is found by your method, by some method, by method A, you can always find x hat. So I will recap these things. You may have any kind of sequence, 0.4, 0.9, 0.6, 0.8, 0.7, and so right. So this is the This is the sequence that you may find by using some method, right? Then we can find x hat right here, and then x hat here by using the previous, and then we can find the new sequence, right? And then we can check whether this new sequence converges faster on one method than the other. Do you follow me? So no matter what sequences are given, you can always calculate Aitken extrapolation, and then you can compare the Aitken extrapolation.
Why can't you just count number of iterations under two methods to see which one converged first?
That one is possible. That one is not very theoretical, but usually that one is algorithmic. In other words, in your algorithm you can do it if you want. Right, counting and then stopping at a certain. But the key idea is Aitken extrapolation itself, as you can see, converges way faster than the original method. And you can compare two different methods. Then essentially done. Then essentially root finding is done. We learned about the different approaches developed by Newton or bisection or Miller or all sorts of things, and we know when the sequence, when the method converges, and finally better extrapolation idea is explained. And now we will go to the next chapter covering integration, and usually integrals represent the area. So we want to integrate a function from a to b, and integrals represent the area when the function is always positive, right, or non-negative. So when the function is always non-negative, then this represents the area. So how to find the area is our focus, and let's do it. So we are using polynomial approach. The function is not necessarily a polynomial. Function could be trig functions or transcendental functions, or even very strange functions. But we are using polynomial approach, and polynomials have order. Order 0 function is flat. Order 0 function is flat. Order 1 function is straight, but it may not be flat, straight. Order 2 function is parabola, right? Order 3 function is a cubic curve. Order 4 function and 5 function, 6 function, and so on. So we want to measure this area by using order 0 function, like this. Right? Then we can develop one method, right? By using order 0 function. In other words, by using a rectangle, we want to measure the area. And second method is using order 1 functions, a little bit slant line, right? So unfortunately, my figure doesn't capture it, so I will sketch different one. Then order 1 function may be better than order 0 function, right? So we are capturing it by using this kind of shape called trapezoid, right? Using trapezoid, we want to capture the area. And second order function is parabola. Using a parabola, we want to capture the area. Third order function, fourth, all these things are possible. So roughly this is the idea, and I will let you know one important thing, unless you have a question up to this point. The important thing is this one. When you calculate the area, we usually need to calculate the area from, for instance, 1 to like 5. So you are asked to calculate area. Then do not use one piece to calculate. That's the key idea you should consider. I saw many people submitting homework doing just one piece calculation. Oh, the area is this. Do not do this way. Then what should you do? You should break up the interval appropriately, at least 10 times, right? At least you should break up the interval. What is going on? Break up the interval. We find enough to have, sorry, somehow it doesn't sketch out. What is going on? I will not break up anymore, but you can break up more. Break up and then apply the idea on thin pieces, right? So this is the key thing. So if you submit homework doing one piece calculation, then I will return you the email asking you to break up. Break up the domain, right? Break up the domain and apply the theorem on this thin piece. And then we add these thin pieces, right? Add these thin pieces. So do not make one huge chunk to calculate the area. But break up and calculate the area of this thin piece. If you magnify it, it may look like this, right? If you magnify it, it may look like this. So this is the magnified portion, not the target. So A to B may be misleading, so I will write down the key, consideration that you need to know. This portion is A plus very small number, very, very small number. Right? This, I magnified it, but it doesn't mean the interval is huge. The interval is very, very small. For explanation purpose, I magnified it, but this piece is very small. Do you follow me? So when you do homework, do not make a huge chunk and then calculate the whole area by just one piece. No. You break up and then calculate the area for each thin piece and then add these areas together to get the total area. So I will pause and then you can check whether you completely understand everything up to this point or not. So let's look at it. So from this point on, I will not return back to this part anymore because I already clarified the matter. You should break up and then calculate the area of this first piece and then second piece and third piece and so on, and after calculating all the pieces, you add up these thin areas to find the total area. Right? That's the thing you need to do. So theory doesn't tell this part very much. Theory focuses on just one very thin piece, right? One very thin piece. But you should not misunderstand the goal of explaining theories, because I don't explain theories to ask you to make a huge, big chunk. I explain these things to show you how to improve your result in the integration calculation. In any case, if you completely understand the point, then I will begin to mention about the approach of using zeroth order function, first order function, second order function, and so on. If you use a zeroth order function, usually zeroth order function looks like this. Zeroth order function looks like this. And the first order function looks like this. Second order function looks like this. Or the other way, right? And the third order function looks like this. So we are using these pieces. We are using these pieces to approximate the area. Then let's look at the shape. I will use one shape and recycle and recycle. I magnify one very thin piece. I magnify a very thin piece here. And to indicate this is thin, I will say this is 0, and this is A, and this is A plus 0.000000000 to indicate the thickness of this rectangle or this shape. I just indicate. In other words, even though shape has huge distance, in reality, these are very close. Then I can use a height, right? The zeroth order function. Then what is the fair way of determining the height? Is this the fair determination, or is this the fair determination? Where can you decide? So fair way might be just choosing the half position of this, half position of this. In other words, we pick this point, half point, right? This half point in the first place, and then check the height here. Of course, it may not be accurate, but at least we don't have any more fairness problem. So this is the height we chose. So this is the approach of zeroth order function, and because of the choice of this, it's called midpoint rule. So this method is called midpoint rule. Do you follow me? Once height is determined, height times thickness, right? Height times thickness will give you the area, thin area, right? Then you accumulate the thin area for the whole interval. So this thin piece plus next thin piece plus next thin piece, and then you can get the answer. So any questions about the midpoint method? So this is the reason why the name is attached, because we chose the middle. So this is the reason why midpoint method name is attached. So let's erase all these things and go to the next method. The next method is the usage of first order function, slant function, right? We can use slant function. Then what is the best way to describe the area using or making a trapezoid? Right? So we are calculating the area of this trapezoid, right? This trapezoid. So this is the reason why the name trapezoidal rule is attached. So we are using first order function to calculate the area. Then what about the area itself? In the first case, in the midpoint case, we calculate the area like this. I will write the midpoint method first. So midpoint, I will explain these things here, and then because we don't have enough space, I will go to the next page and begin to summarize all the details. But right here, I'm just explaining. Then we can calculate the area of this trapezoid, right? Area of this trapezoid. Area of the trapezoid is not difficult to calculate. The next method is using a parabola passing through the strategic point. Using parabola passing through the strategic points here. So usually, parabola requires 3 points to anchor. 3 points to anchor. So let's pick 3 equally divided points. First point here, second point here, and the third point here. And then we can find a parabola passing through these 3 points. Very huge parabola. Very huge parabola passing through these 3 points. So very huge parabola here passing through. Somehow this is the part showing here. Huge parabola passing through this point. So this is a piece of huge parabola passing through. Then we can do the integration, because parabola is a second order function, and then second order function can be integrated. Second order function can be integrated from a to a plus 0.001, right? So this function can be integrated. Do you follow me? It's straightforward calculation. Second order function can be integrated straightforward. And you can do the same thing with third order function, fourth order function, and depending on the order, we may get different formulas. But I don't want to go through all the formulas because I already summarized all the formulas on the summary note. But the idea part is completely explained here. And if you don't have questions, then I will begin to summarize a few cases and then go to the next case. So please browse the idea and let me know. Then save it, and not just here, save as, because in the past we lost the nodes. So what about the small piece? Small piece is this one. Area of the small piece in zeroth order function. Zeroth order function gives us midpoint rule, right? Midpoint rule. Then we pick the middle point of the two. So let's not be too extreme. Right? Let's not be too extreme, right? Then we should calculate the height at a plus 0.005, right? So we should calculate calculate height at this point. The function is given by the problem. Usually the function is f of x. The height here is what? The height here is f of a plus 0.005, right? This is the height. This is the height. So what is the area? So this thin area equals f of a plus 0.005 multiplied by this length 0.01. So this is the area of this thin piece. Then this kind of area is accumulated from the left side to the right hand side to find the area. In other words, the total area equals this kind of thing added, right? Sum of these kind of things, or f of a plus 0.005 multiplied by 0.01, first piece, and then second piece, f of a plus 0.015 multiplied by 0.1. Right, this is the second piece. And the third piece, f of a plus 0.025 multiplied by 0.01, and so on, right? We can go all the way through b, right? So final point might be f of b minus 0.005 multiplied by 0.01. So this is the total area from A to B. So we are calculating the area from A to B using step size 100, right? 100. So using 0.01 step size, we accumulate the thin areas this way. Any questions? Then the next thing is the trapezoidal rule. And as you saw here, we don't have to write down these things over and over again. Just some generic piece might be enough, right? So I will write the generic piece, then we somehow copy the generic piece accordingly, right? So what about the method for the trapezoidal rule? If you use the first order method, then it becomes trapezoidal rule. Then this method uses this thing, right? Uses this thing. So I will use way better, way rougher increment. Instead of 0.01, I used 0.1. So I decided to use this piece from A to B. Then, what is this height? This height is what? F of what? A. What is this height? F of A plus 0.1. Then what is the area? With these things, can you calculate the area? Area of the thin piece is what? Average of the two, A plus 0.1 over 2, average of this height multiplied by the width. Right? Multiplied by the width. So this is the area of the thin piece. Then we accumulate this thin piece from A to B. Any questions? Now the third order requires some calculation. because of this reason, instead of going to third order right now, I will write the total area one more time. Total area is this, equals this thing. 1.1 is multiplied all the way through, so I will just extract the common factor. 0.1 width, right? 0.1 is multiplied all the way through. So I will just write these pieces. F of A plus F of A plus 0.1. And the next piece is F of A plus 0.1 plus F of A plus 0.2, right? And then all the way through. Unfortunately, we cannot extend it anymore, so I will just write the result. F of B minus 0.1 plus F of B over 2, right? Over 2, done, right? Over 2. So this is it. So this is the result of the area. So let's take a break by this clock until 3, and then we will resume at 3.